All right, everybody. So we finished up to section 4.5 in chapter 4, and we looked at the simplest alkanes. So we started with methane, which is CH4, and then we added one carbon to that, and that gives us ethane. And you should know that around a carbon-carbon bond that we have free rotation, right? There's always free rotation around a carbon-carbon bond. I do have a model with a pi bond in it. I'll just show you quickly. If you have CH2, CH2, you can see there's a pi bond here, and there is no free rotation around a pi bond. It's only around single bonds that we have free rotation. And so with our ethane molecule, we can rotate that. Then if we could add a third carbon to that, and that would give us a propane molecule. Then we could add another one to it, and that would give us a butane molecule, so on and so forth. Okay, but where we're going to start out right now is by talking about what's called a Newman projection. And if you look at the molecule of ethane, CH3CH3, if you look down this carbon-carbon bond with your eyeball, what you're going to see is something that looks like this. Okay, you can see that all the hydrogens are spread out from each other as much as possible the way I have it. But I told you that there's free rotation around the carbon-carbon bond, and so they could all be blocking each other out like this. We call this conformation an eclipsed conformation, where there's no angle between the hydrogen in the front and the back. We call that angle the dihedral angle, and I have that in my slides. If I rotate this bond those 60 degrees, then I get what's called a staggered conformation. And a staggered conformation is going to be lower in energy than this conformation here, which we call an eclipsed conformation, where everything is blocking each other out. And the reason why this is going to be higher in energy is because you have electrons in all the bonds, and they're closer to each other, so they're repelling each other. And so if I bring it over to the staggered conformation, it becomes lower in energy. So we could visualize this molecule kind of tilted on its side like this. We call that a sawhorse representation. But if you turn it right on its end, we would call drawing what you're seeing right now on the screen, we would call that drawing a Newman projection. And that's what we're going to take a look at right now. So just bear with me here, and I'll find the slides, and we'll take a look at it. So our slides are right here. There we go. So in section 4.6, we're going to discuss how to draw these Newman projections. And like I told you before the break, they were developed by Melvin Newman at Ohio State University. So we took a look at the molecule, the ethane molecule, which is CH3. We viewed it sideways, and we would draw that. And when we draw that, we would call that a wedge and dash model, where we use dashes to show bonds that are going back into the page or going away from you. And then we use wedges to represent bonds that are coming towards you. Then if you tilt it slightly, you end up, so if you rotate it slightly, you end up with what's called a sawhorse diagram. We're not going to use those a whole lot in this class, but if you were to rotate this bond 180 degrees, 90 degrees, you would end up with what we call the Newman projection. So you're literally taking your eyeball, so this is a human eyeball, okay, and you're looking down this carbon-carbon bond, and what you see is something that looks like this. So the way that we represent it, the carbon that's in the front is represented by the junction of the three bonds here, and the big circle in the back, that represents the carbon in the back. Okay, so carbon in the front, carbon in the back. So this carbon and this circle represent this carbon in the front, this carbon in the back, but that represents the two carbons in the Newman projection. Why are we so concerned with Newman projections? Because they're ideal for comparing the relative stability of conformations, the eclipsed conformation being higher in energy and the staggered conformation being lower in energy. So let's move along, and it says a Newman projection is the perspective looking straight down a particular carbon-carbon bond. And so if we were to turn our eyeball to look down this carbon-carbon bond, what are we going to see? Well, there's three hydrogens on the two carbons in that I have highlighted in yellow that aren't shown, aren't there? Right? We have a hydrogen going in the back here, and then we have another hydrogen on a wedge here because this one is coming out in front. This is a methyl group. And then we also have a hydrogen coming out in front like this. Of course, this is a CH3 group, but we're not looking down that axis. So what I'm visualizing is that the viewer is standing in front, right? You can imagine that you're kind of standing in front here, looking down this carbon-carbon bond that I'm highlighting in yellow. Now, the carbon in the front, okay, this carbon here, that's this carbon here, and the carbon in the back, the one in blue, that's represented by this circle that I'm highlighting in blue right now. So if I name or just letter these two hydrogens, I'll call this HA and I'll call this one HB. So based on me looking down that carbon-carbon bond, could anybody tell me if I highlight this proton in yellow, would that be HA or HB? If it's going to the left. So think about the way the viewer is standing. If you draw the whole viewer, right, that's going to be HA, right? If you draw the person, so here they are, right? So here they are, right? So there's their mouth, right? So they're looking down the bond, and this HA is going to be the one on the left. HB is going to be the one on the right. And then in the back, you see the methyl group is going towards the left, right? It's going into the page. And then if we call this one HC, well, obviously this is HC here. So you need to be able to draw a Newman projection. I'm going to erase this before anybody sees it. There we go. All right, let's move on from there and let's try drawing a Newman projection. So we have the carbon-carbon bond we're interested in. So I'll just put a little red dot here. So that's the carbon in the front. The carbon in the back, I'll put that in blue. So there's my carbon in the back, and then I have my carbon in the front. All right, so in the carbon in the front, we're going to have a proton going in the back, and then we're also going to have a proton coming in the front. Now here, there's two chlorines, so it doesn't matter whether one's drawn in the front or in the back. It doesn't matter at all. I'm just going to spruce it up and put a dash on this one and a wedge on this one. And then, of course, here I have a methyl group, and here I have another methyl group. All right, so what is the viewer seeing? Well, if we look at the carbon in red, you can see that in the plane of the line of viewing, the viewer is seeing the methyl group going straight up, right? There's a methyl group going straight up like this. Then there's going to be two bonds, one like this, oops, and one coming down like this. Could anybody tell me, if I label this proton as HA and this one as HB, where I have highlighted in yellow, would that be HA or HB? Based on the way the viewer is seeing it. It's going to be HA, isn't it? Right, so I have HA here. I'll call this HB. Then in the back, I'm going to have 1, 2, 3 bonds. Now, what's going straight down? What's in the same plane of the viewer? Well, you can see that all of this is in the same plane. Everything I have highlighted in yellow, there's no dashes or wedges on that. So this would be, excuse me, this would be our methyl group down here. And then I'm going to have two chlorines like this. Right, if I called this chlorine A and I call this one chlorine B, this would be chlorine A and this would be chlorine B. Give me a thumbs up if you're with me on that, on drawing a Newman projection. It's a big deal, being able to draw a Newman projection. Heck yeah. Is it something that has to be practiced? Absolutely. You have to practice Newman projections in order to master them. There's no kind of shortcut around a Newman projection. And so what I want to do now is switch over to a blank document with you, and we're going to try to draw another one here. So what if I gave you something like this? So this one also comes from question 4.16, I think, in the textbook. Let's try a different angle maybe. Let's say you had this molecule, you have a chlorine in the back, and then you have a bromine coming out in front like this. But let's say you're viewing it down this axis, right? Going from here to here. So I'll put this carbon in red and this carbon in blue. So the carbon in red, we got a little dot like that. The carbon in blue is going to be the circle behind it. Okay, so what's in the plane of the viewer? Well, let's see. There's going to be a methyl group going straight down. So we're going to draw a methyl group going straight down off of here. Then we're going to have a bond here and a bond here. All right, so let's see. We have the chlorine that's going into the page, so that means there's going to be a hydrogen coming out of the page. So if I highlight this group in yellow, which is going to be out here? Would it be the chlorine or the hydrogen where I have the yellow highlighter? Exactly, it's going to be the chlorine, isn't it? So this is my chlorine, this is my hydrogen. In the back, I've got another methyl group here that's going to be going straight up like this. So I'll put methyl group here. Then I have something coming down here and something coming down there. So I've got the bromine. Which side is the bromine going to be on? Would it be on the left-hand side or the right-hand side at the bottom? So is the bromine on the left or the right? Yeah, absolutely. The bromine is going to be on the left-hand side, right? And then there's a proton that hasn't been drawn in. We'll just put it in, and that is the proton right here. And there you go. So that is how you draw a Newman projection. Very important. Newman projections come up a lot in organic chemistry. You probably noticed that I mentioned the angle between substituents like this. We call this a dihedral angle. So dihedral angle. And of course, that angle, if everything is completely staggered, that would be 60 degrees. What's shown here. Anyhow, I digress. Let's go back to the slides, and I'll show you exactly what I'm talking about here. So let's see here. There we go, chapter 4. Where were we? Somewhere around here. Let's go back from whence we came. All righty. So we got some practice on this one and this one. And now we're at what we call the dihedral angle. Dihedral angle has two names, actually. It can be called a dihedral angle or a torsional angle. They mean the exact same thing. Now, the dihedral angle shown in this ethane molecule here, right? This is nothing more than a molecule of ethane. So we have a hydrogen here, one in the back, one coming out here, one in the back, and one coming out here. And the viewer is looking down this bond. Okay, this would be the carbon in the front, right? This would be the carbon in the back, right? Which is this guy right here. All right. So the dihedral angle is 60 degrees. But like I told you, there is free rotation around a single bond, or what we call a sigma bond. There's free rotation around that. And so if we rotate that bond 60 degrees, all the carbons and hydrogens are going to be blocking each other, and we call that an eclipsed conformation. So to repeat, the staggered conformation, where we have the biggest dihedral angle, which is 60 degrees, is going to be the most stable, and the eclipsed conformation, where I have a dihedral angle of 0 degrees, okay, and they can't show it completely blocking each other out on the slide, or it wouldn't be really difficult to make sense of that, but we call that the eclipsed conformation. So there's actually a difference in energy between these two due to the torsional strain, where you have, bonds really close to each other, and that is 12 kilojoules per mole. So somebody asked me in the chat, how do you know what is going into the page and out of the page? So if we go back here, when we have a dash, right, when the line is dashed like this, this is going into the page, going in. And when you have a wedge, this means it's coming out. So coming out of the page, right? And we call that one a wedge, right? And we call this one a dash. All right, so a dash is going into the page and a wedge is coming out of the page. All right, so torsional strain. Yes, it totally matters what element is going in or out. Yes, right? It just depends on the molecule. It depends on the way it's drawn. All you need to do is to be able to go from the wedge and dash structure to a Newman projection. That's what you've got to be able to do as a student in the class. So if we look at the conformational analysis of ethane, if we take that molecule and we start rotating the carbon-carbon bond, right? So all I'm doing is taking this molecule, okay, this guy right here, see if I can bring that over, copy, see if we can paste it in here somewhere. Paste it right there, okay? All I'm going to do is take this molecule, just going to erase some of this spinach here, and then I'm just going to rotate the carbon-carbon bond. All I'm doing is rotating this bond in red, rotating it, spinning it around and around and around. And you can see that I have two types of conformations. I have staggered on the bottom, which are lower in energy, then eclipsed on the top, where everything is blocking each other out. So it says, notice that all the staggered conformations are degenerate and all the eclipsed conformations are degenerate. Remember that in chemistry, the word degenerate means equal energy. Equal energy. Right? That's something you would have seen in General Chemistry 1 when you talk about degenerate p orbitals, right? Orbitals that have the same energy. All right, so there you go. So that's the conformational analysis of ethane. So what I'm going to do now is I'm going to try to switch over to my camera. Just bear with me here for a second, and I'll share a video. Let's see if this will work. All right. Hopefully you can see my model. This is my ethane molecule here. So the idea is this. When it's going to be staggered like this, it's going to be low energy. Then we eclipse it, and it's going to be higher in energy. If we stagger it, it's going to fall back down in energy. And then when we eclipse it, it's going to go back up in energy. Are you with me on the idea of eclipsed, high energy? And when it's staggered, it's going to be low energy. Give me a thumbs up if you follow me on that one. Cool. All right. Well, what happens if we add a carbon to that? Then we have a propane molecule. So here's a molecule of propane. So this is CH3, CH2, CH3. If we do the same thing now, if we look down one of the carbon-carbon bonds, it doesn't matter if it's this one or this one, we get the result no matter what. But if we look down one of the carbon-carbon bonds, you can see that we have two possible conformations. We can have staggered or we can have eclipsed, okay? So the eclipsed is going to be higher in energy, and the staggered is going to be lower in energy. If we eclipse it, it goes back up in energy. If we keep rotating, there we staggered, lower in energy, eclipsed, higher in energy. Okay, so the exact same thing. The only difference is that now you're replacing one of the hydrogens with a methyl group, right? This is ethane. We added a methyl group to make propane. So let's go back. Let's see. Let's go back to the slides and take a look at the conformational analysis of propane and ethane, what we were just looking at. So here we see the conformational analysis of ethane, and you see the difference between the staggered and eclipsed conformations is about 12 kilojoules per mole. But when you do the same analysis for propane, it is increased by 14, or it goes up to 14 kilojoules per mole. Notice that all the eclipsed conformations are degenerate, they're equal in energy, and all of the staggered conformations are equal in energy as well. All right, so there we go. So we've analyzed the conformational analysis of ethane and propane, but what did we learn from propane? We saw that there's more, or that the eclipsed conformation with propane is higher in energy than that in ethane. And it says here the barrier to rotation is 14 kilojoules per mole, which is two more than that for ethane. So what that means is that every proton-proton eclipsing interaction costs a total of 4 kilojoules per mole. If we have two of them when we're eclipsed with propane, that makes a total of 8. If you take 14 and subtract 8, what that tells you is the value of the eclipsing of a proton in a methyl group is 6 kilojoules per mole. So it's a little higher in energy. I'm not going to ask you to do any calculations with that or anything of that ilk, but the rationale still stands, and you should understand where the numbers come from, okay? All right, so let's make it even more interesting. Now check this out. If you look at the conformational analysis of butane, you'll see that all of the eclipsed conformations are not degenerate, are they? All right, you have two that are equal in energy, and then you have one that's higher in energy. All right, and there's a good reason for that. If you look at the one that I have highlighted in blue, you see that in that particular eclipsed conformation that you have two methyl groups blocking each other, whereas the other ones, it's just a methyl and a hydrogen blocking each other, right? That's all we have, and the other ones are methyls and hydrogens blocking each other. But here you have two methyls, those are bigger, so it's going to cost you more energy. The same thing occurs when we look at the staggered conformations. You see that we have a total of 4 of them here, but they aren't all equal in energy, are they? We see that you see the ones where the methyl groups are as far away from each other as possible are lower in energy than the ones where the methyl groups are close to each other. And we call this a gauche interaction, when you have something close to each other and it causes them to be higher in energy. So when they're far away from each other like this, we call this anti. And when they're next door to each other like this, we call it gauche. So G-A-U-C-H-E. So gauche interaction, and then we have anti as well. So if you didn't catch it on the last slide, here it is. if we look at the conformational analysis of butane, so all we're looking at on this slide is butane, and if you view it down, this carbon-carbon bond, okay, what are the possibilities? You have an anti-conformation, which is the lowest in energy. Then you have two other staggered conformations, but now you have a gauche interaction where there's going to be a steric hindrance between the two methyl groups being next door to each other. So I'm going to go to this back to the screen one more. My butane molecule. So just bear with me here. I'll switch back. And just let me build my model here. So share video. All right. So if I make a butane molecule, like this. All right, there's my butane molecule. I'm going to look down this carbon-carbon bond like that. So we see this is the gauche conformation. Okay. Then if I take it to the next staggered conformation, so this is still staggered, but now you have the, did I say it was gauche? Okay, so this is anti. Okay, this is the anti conformation. The two methyl groups are as far from each other as possible. Then if I bring it to the next staggered conformation, like this, now I have the gauche effect of this methyl group in the front and this methyl group in the back where my finger is, right? They're kind of close to each other. If I go to the next staggered conformation, you see that we still have that gauche interaction right here between this methyl group and the one in the back. And then if I bring it to the next staggered conformation, which is anti, the two methyl groups are as far apart from each other, so this one's going to be lower in energy. If I look at the eclipsed conformations, I have one like this, okay, where the methyl groups aren't touching each other or aren't close to each other, and then I have another one where the methyl groups aren't close, and then I have this one here where the two methyl groups are next to each other, and this one is going to be the highest energy, or highest in energy, of all the eclipsed conformations. Sorry, my chair is so squeaky. My office chair. All righty. Any questions about that? With the whole idea of staggered and eclipsed and gauche and anti, because these are terms that you're going to have to know. All right, well, let's move on from there and let's talk about cycloalkanes for a few minutes. You guys probably remember when you talked about tetrahedral molecular geometries, the preferred molecular geometry or bond angles for an sp3 hybridized carbon. So if we have a carbon and we have 1, 2, 3, 4 groups, we'll just make methane, okay? The ideal bond angle is 109.5 degrees. Our textbook goes into some interesting history about bond angles, and the whole idea is that chemists used to think, well, if you go from cyclopropane to cyclobutane to cyclopentane to cyclohexane, that the molecules are flat. They thought they were flat like a piece of paper, and so they said, well, the one that has the closest to 109.5 would be the pentagon. If you measure the bond angle inside a pentagon, it's 108 degrees. But then they ran into a serious problem when they made the assumption that the cycloalkanes were flat, is that this one is not the most stable. It in fact turns out that cyclohexane is the most stable, even though the bond angle inside a hexagon is 120 degrees, significantly larger than a tetrahedral bond angle. So this gave them some serious pause, and they thought about it, and they said, well, this doesn't make any sense. So if you take a look at the heats of combustion per methylene group of cyclopropane, cyclobutane, cyclopentane, cyclohexane, what you see is that the one that's going to release the least amount of heat per CH2 group is cyclohexane, right? This one is the most stable of all. Don't worry about cyclododecane. Don't even think it. We're never going to talk about this. But the reason why cyclohexane is the most stable, there's a very good reason for that. It's because we know that molecules are not flat, are they? No, we know that they have a three-dimensional shape. And so you can see cyclopentane is pretty stable and cycloheptane is not that unstable, but cyclohexane is definitely takes the star, right? It definitely takes the gold star. It is the most stable of all of them. And we're going to look into why that is in just a second. But where we're going to start is by talking about cyclopropane and cyclobutane and why they are so high in energy, why they have such a large heat of combustion per methylene group. So this is cyclopropane right here. So cyclopropane, right, which is this, okay? And over here we have cyclobutane. Yeah. Cyclobutane, which is this compound. Okay, so why are both of these having such high heats of combustion per methylene group? It's because they're highly strained. Okay, they're just very highly strained. The book goes into some detail about this. I'm not really going to quiz you about the strain. It's not really something I'm super interested in. But the idea is if you try to make a model of cyclopropane, I mean, that's going to break your model. Okay, I can't even do it with my models. It will not work. Okay, I can't even make one with, I can't even make a cyclobutane. But the idea here is that if you look down any one of these carbon-carbon bonds, okay, if you look down this carbon-carbon bond going this way, is that everything in here is eclipsed. Okay, so that's really high in energy. And you can see how the hybrid orbitals have to kind of bend towards each other. So that's all I'm going to say about that. If you look at cyclobutane, it can adopt this kind of puckered conformation where the bond angle is about 88 degrees. And that puckering prevents some of the eclipsing from occurring, but it doesn't do a great job. And so it's still going to be really high in energy. Once we get to cyclopentane, so what we're seeing here is a model of cyclopentane, this guy here. Cyclopentane is actually a pretty stable molecule. I can make cyclopentane with my model kit. And what it does is it adopts what we call an envelope conformation. And so the bond angles are close to 109.5, but there's still some torsional strain, even though the envelope conformation avoids most of it. So let me go back to my camera here, and I'll show you what I mean with my model of cyclopentane. So here's my model of cyclopentane right here. Okay, so this is 5H10. And what it does is it adopts this envelope conformation, right? So you can see how you have kind of the bottom, and then this part's the top you would fold over the top. That's what they call an envelope conformation. So if you look down one of these bonds, right, you can see that it's quite staggered if we look at it like this, right? If you look at the other ones, though, they're going to have more eclipsing. But the bottom line is that this thing is always moving. Okay, it can move, and what that does is it can relieve a lot of the torsional strain. So it does some eclipsing, or sorry, some staggering there. Anyhow, what happens if you add another carbon in the ring? So here's carbons. I'll add a sixth one here, and we'll tie it up. And this is going to be the focus of a lot of our lecture the rest of the day, and we get a molecule of cyclohexane. If you look at it this way, you can see that it looks just like a hexagon, okay? C6H12. But check it out. When we hold it like this, it's not flat, is it, right? And this is what we call a chair conformation that you see in here, okay? This kind of looks like a chair. You'd kind of sit your tuchus right here, lay your back up here, and then you'd kind of lean your head back here. Call this the chair conformation. What do you notice about every single carbon in C6H12? Does anybody notice their molecular geometries? They're all perfectly what? Everything in this molecule is perfectly tetrahedral. Every bond angle in cyclohexane, every single bond angle in here, this angle, every angle is perfectly 109.5 degrees. And that's why cyclohexane is such an important compound. All right. So not only do we have this conformation, we call this the chair. You can actually flip the chair by rotating the bonds, okay? And another thing I want to show you are some different positions. Did you notice that 3 of the hydrogens are pointing straight up and 3 of them are pointing straight down? Whether something's pointing straight up or straight down, so if it's vertical, we call that axial, an axial position. So we have 3 protons that are axial and pointing up, and then we have 1, 2, 3 protons that are axial and pointing down. If you look at the middle of the ring, you notice that you have 1, 2, 3 protons that are what we call equatorial, so in the middle, and they're pointing down, and then you have 1, 2, 3 that are in the equatorial region that are pointing up, okay? So another thing is that you'll notice is that it alternates. If you have axial and up, the next one is axial and down, axial and up, axial and down, axial and up, axial and down. And the same thing occurs for the equatorials. You go equatorial up, equatorial down, equatorial up, equatorial down, equatorial up, equatorial down. So we have a total of 6 protons pointing up, 3 of them are axial, 3 of them are equatorial. We have a total of 6 protons pointing down. 3 of them are axial, 3 of them are equatorial. Is that enough information for you? Anyhow, there's our chair. Another thing I want to show you is about flipping the ring, which we're going to get to in just a few minutes here, is that when you flip the ring, okay, anything that was axial and pointing up, like we have we'll call this an oxygen, when you flip the ring, it's still pointing up, right? The bond is still going up, but now it's equatorial. So when we flip a ring, anything that was axial becomes equatorial, and anything that was equatorial becomes axial. So when I say flip the ring, I actually mean rotate sigma bonds. That's what I'm doing here. I don't mean flip it like a pancake. That's nothing, okay? That's not flipping a ring. Flipping is rotating sigma bonds. So I go from one chair to the other chair. All right, there you go. So a lot of information there. Are you going to have to read it? Yes. Might you have to buy molecular models? That depends on the person. All right, so let's go back here. And let's talk more about this whole idea of the CHEM, all right? Okay, of cyclohexane. So I said that when you have a cyclohexane molecule, so draw a cyclohexane. I'll draw my best hexagon that I can. This is C6H12. We know that every carbon in here is tetrahedral, and so we can draw it as a chair. And drawing a chair is a skill, and I'm not saying Mr. Dion's the best because I'm not, but that's a pretty decent chair. And then if you flip it, so if you flip the ring, so flip, what you're going to do is you're going to reverse the chair. So it's going to look like this in that case. Okay, so there's a chair. I flipped it, and you end up with another orientation. So if I have a group that's up and axial, okay, when I flip the ring, it's still going to be up, but it's going to be up and equatorial. All right, and there's other conformations besides a chair. The chair is the most stable of all the conformations of cyclohexane. I didn't show you with my model kit, but there's one called a boat, and you have the twist boat and half chair. I'll be honest with you, the only one that you're going to worry about in this class are going to be the chair. Okay, that's the only one you need to worry about in this class, and you should learn how to draw a chair. How are you going to do that? Practice, really. Okay, and Dr. Klein has a tutorial, a way to do it. I have my own way. I worked in a carbohydrate lab, so I kind of learned working there. But again, why is the cyclohexane molecule so important? It's because there's no angle strain. Every bond is 109.5 degrees in a cyclohexane molecule, everything. There's no torsional strain. I forgot to show you, but if you were to look down any of the carbon-carbon bonds like these two, what you would see is this. Okay, you see that the Newman projection shows you there's no strain whatsoever. Everything is perfectly staggered in there. So there you go. All the other conformations like the boat, the twist chair, the half chair, and all that stuff, they all have some kind of ring strain. So again, this is why cyclohexane is such a big deal. Now, how are you going to learn how to draw a chair? I suggest just getting a blank piece of paper and just practicing it over and over. You know, practice drawing a chair. Okay. So practice drawing a chair. Not the best chair in the world, but not the worst. And then you can practice drawing in all the axial positions. So wherever you have a point going up, you're going to draw straight up from there. So there's the 3 positions that are up and axial. Let me fix this one like that maybe. Then you have 3 positions that are down and axial. 1, 2, and 3. Okay. Again, it's not the best chair in the world. Then you have all the equatorial positions. So you have one that's going up and equatorial here, one that's down and equatorial here. This one is going to be up and equatorial. This one's going to be down and equatorial. This one's going to be up and equatorial. This one's going to be down and equatorial. Okay? And you really need to practice drawing in all of those different positions. And if you've noticed that every time so usually students struggle with the equatorial positions, the ones that are in red. But what happens is if you look at any of the equatorial positions, maybe I'll use my yellow marker. If you look at any of them, then you go 1, 2 bonds away on the ring, you see lines that are parallel, right? So you can see how those 3 sets of lines are parallel. Like you can see I didn't do a very good job on, say, this one here. this bond in red, it should be more coming up kind of like this, I guess, because this bond should be parallel to this bond and this bond. All right. So if you're wondering, do you have a slide for showing how to draw a chair? Yes, this is Dr. Klein's way of doing it. This is from David Klein, the man himself. Okay, this is his method, the drawing a wide V or whatever. I'm going to let you figure this one out yourself. I don't say that a lot, do I? I don't usually say, oh, just figure it out. Well, you kind of have to figure out how to draw a chair yourself. It's like drawing anything, really. You can use his technique, which is shown here, where you start with a wide V and then just draw a set of parallel lines kind of thing. Or you can do it my way, which is the way Frank Sinatra did it, right? No, that's not good. You just practice over and over until you get a chair that you think looks decent. One thing that my students will do sometimes, not you guys, you would never do this, but they'll draw something that looks like this. Okay, this is nothing. Okay? This is a bow tie. Okay, that somebody would wear, to a wedding or something. That is not a chair. Okay, so do not draw a bow tie. Anyhow, it's nothing, a bow tie. All right. Well, let's go back here. So he says, if you draw a chair correctly, you should have a set of 3 parallel lines. Again, if it's drawn correctly, and do your best, right? Again, we have axial positions. Those are the ones that are going straight up or straight down. And then then you have the equatorial positions, which lie in the equator, kind of, or the center of the molecule. All right. And when you're adding the axial substituents, this is another thing. So if you have 2 lines coming together at a point, right? This one's going up and this one's going up towards a point. So that means the axial position is going to be going straight up. Right, you have this one that's coming down this way, this one that's coming down this way to a point. So the axial position is going to be going straight down. Right, let's say you have this one that's going up in this direction, this one's going up. So that means the axial position is going to be straight up from it, right? Let's try this one here. You have a line going up this way, a line going up this way. So the axial position is going to be straight up. Right, you have a line going down this way. You have a line going down this way. So the axial position is going to be straight down. And that's how you draw axial positions. And then the equatorial groups, I already showed you this, that if they're drawn correctly, they should be parallel to lines 2 bonds away, right? So if you have this thing, for example, drawn correctly, right, you go 1, 2, and it should be parallel with this, and it should be parallel with this line too. Now, you can see, hopefully you see things from my point of view as your instructor. This is one of those things, there's only so much yammering on I can do about draw a chair, everybody, I'm sure that some people can draw it better than me in the first time they do it. And I'm sure there's other people that struggle with it. Maybe think, I'm not a great artist. Well, it's one of those things. We have to practice drawing our chairs. It's something that it's one of those things that all organic chemists must pass through. So there you have it. So if we go back to the idea of flipping the ring, remember, when you're flipping a ring, you are not flipping it like a pancake. What you're actually doing is rotating sigma bonds. So when you flip a ring, anything that's axial, so you can see that this is going up and axial, anything that's axial becomes equatorial. But the direction does not change. If it's up, okay, when you flip the ring, it's still going to be up. Okay, it might not be pointing straight up, but it's still pointing up. Anything that was down is going to be down. Let's practice. If you had a group here going down, okay, see here going down like this, you would call that group Y. Well, now here it's going to be down, but it's going to be axial, right? So when you flip the ring, anything that's axial becomes equatorial. Anything that's equatorial becomes axial, so on and so forth. So if we look at methyl cyclohexane, it says, if you took a sample of methyl cyclohexane and you looked at the equilibrium, that the methyl cyclohexane exists 95% of the time in a conformation where the methyl group is in the equatorial position. Now, there's got to be a reason for this. Why is it mostly lying to this side? Okay, and there's a very good reason for that, and it's based off of Dr. Oppenheim's favorite thing, which is sterics. Okay, if you had Dr. Oppenheim for Gen Chem 1 or Gen Chem 2, he always gives me a hard time about sterics this and sterics that, Dan, right? So what's going on here is when it's in the axial position, the problem is that you have another hydrogen here that's axial and a hydrogen here that's axial. And that creates some steric hindrance between these groups. We call this a 1,3 diaxial interaction. If you're wondering, well, where does the 1,3 come from? It comes from this. 1, 2, 3, and 1, 2, 3. Hence the name 1, 3, and both things are axial, 1, 3. So we call this a 1, 3 diaxial interaction. All right, there we go. So the 1, 3 diaxial interaction. And really, the 1, 3 diaxial interaction is nothing more than a gauche interaction. Okay, I'm going to highlight that for you. All it really is just a gauche interaction. Okay, nothing more than that. I'm not really going to quiz you on, oh, is it a gauche interaction or whatever, but that's really all it is. It's nothing more than that. So if you were to look down one of the carbon-carbon bonds of a cyclohexane, or two of the carbon-carbon bonds. So let's say you drew, let me just draw a chair over here. So Mr. Dion's, I have a hard time drawing in the corners of the iPad. So you drew a chair like this. So if you were looking down, this bond and this bond, so this would be the one in yellow, right? Then this would be the one in red, right? You're looking down those two bonds, and what you see, if you have a methyl group, so the methyl group would actually be here. Yeah, it would be right here. This is the CH3 group. That's this one right here. You would see that the methylene in the back, okay, you have no 1,3 diaxial interactions in this conformation, but if it was axial, then you would have the 1,3 diaxial interaction there. Anyhow, again, I'm not going to quiz you on that a whole lot. All you need to know is if something is in the axial position, it's going to be less stable than something that's in an equatorial position. That's good enough for Mr. Dion. All right, monosubstituted cyclohexanes. You can imagine that when you have a group on a cyclohexane, so if you have a cyclohexane and you have a group, okay, we'll call this group X. We'll just move this around. Come on. I move this guy over here a little bit. Okay, you can imagine that the bigger the X is, okay, the bigger the substituent is, the greater the cost of the energy of the 1,3 diaxial interaction between it and the neighboring protons. So we go from a chlorine to a hydroxyl to a methyl. Those aren't too bad. Then you get up to an ethyl and an isopropyl, and then you get up to a tert-butyl. Okay, tert-butyl. And if you have a tert-butyl group, it's so dang big that you almost have none of it in the axial position. It's virtually all going to be in the equatorial position, right? If you flip the ring, whatever it is going to go from axial to equatorial, right? Because the equatorial position doesn't have those 1,3 diaxial interactions. All right. So with that, I think we're going to take another break, and then we're going to come back and look at disubstituted cyclohexanes.